আমরা আমাদের কোর্সের ডিটেলস সম্পর্কে আগেই জেনেছি আমাদের হোয়াটসঅ্যাপ গ্রুপে। আমরা আমাদের কোর্সের রেকর্ডিং এবং যে কোনো ডিসকাশন হোয়াটসঅ্যাপ গ্রুপে করতে পারবো, আর রেকর্ডিং গুলো হোয়াটসঅ্যাপ গ্রুপে দিয়ে দেওয়া হবে। আর কোর্সে হচ্ছে সার্টিফিকেট এনশিওর করার জন্য আমাদেরকে হচ্ছে 80% অ্যাটেন্ডেন্স মাস্ট মেনটেন করতে হবে, তাহলে আমরা সার্টিফিকেটটা পাবো।
So, good morning, dear students. Can you listen me?
Yes, sir.
Okay.
Yes, sir.
So, welcoming you all here in today's short course on ANSYS. And within this small tenure, this is quite difficult to actually elaborate all the informations on the ANSYS. But here we will actually try to give you a very small introduction and also show you some of the basic features of this ANSYS Fluent. And I'll be your instructor for today and tomorrow. And I will try to cover some basic steps of the ANSYS and also your fundamental understanding that why we use ANSYS. And I think then things will be quite clear for you by the end of the course. So any type of questions are welcomed. And as most of you are from nuclear engineering background, we will actually try to relate this as much as we can with the nuclear engineering topics and from the point of view of nuclear thermal hydraulics. So would you be able to download or install the ANSYS file in your laptop or in your desktop? So how many of you have the ANSYS installed in your laptop or desktop? I can see there are total 35 participants right now. So can I say that most of you have installed ANSYS in your laptop or desktop, or I can say that most of our, okay, no sir, not yet. Okay, so
No, sir, I can.
okay, did you try? Okay,
Yes,
so
sir.
mm-hmm.
It take times.
Okay, so there are actually two versions right now that is actually available for ANSYS. First one is the ANSYS student version. In ANSYS student version, this one is actually a free version, and in the official website of the ANSYS, you can find this ANSYS student version. So you can actually start downloading this ANSYS student version after today's session, because this class will be in recorded form and you can also check from the recording and then you can practice. But whatever, why actually we actually cannot use the ANSYS student version during our real life scenario or during our thesis project, because in ANSYS student version there are some limitations, and because of these limitations you cannot actually get the exact result from this ANSYS student version, which is actually the official version. So that's why we have to actually take another way to use the crack version that we actually suggested to download from the torrent. Though this is not advisable, but we have to do this because we don't have the official version right now with us. So I will provide another link from where you can actually download the ANSYS student version, and you can do some practicing. So and the version that I asked to download, it was ANSYS 16. This is actually quite compatible, and the later versions are actually the cracked versions are not doesn't work properly. So we actually move on with this older version of ANSYS 16. So before we actually proceed, we actually want to show that how this ANSYS and this computational fluid dynamics is actually related with nuclear engineering. So can you please actually tell me that how these are related? Can anyone please tell me? What is your understanding? How computational fluid dynamics is related to this your field? How you actually can relate this computational fluid dynamics, and how you can actually use ANSYS in your particular field? Suppose you are interested in VVR 1000 or VVR 1200 reactor, or you are interested in the turbine, or you are interested in the AP 1000 reactor. So how you can actually incorporate this ANSYS CFD or ANSYS fluent in your interest? Can anyone please share?
So it is mainly needed for thermal hydraulics analysis. Let us suppose that we want to analyze velocity profile in a hot leg pipe. Then we can construct a pipe in pipe in ANSYS. Then add water as fluid. Then run the simulation. We can get the velocity profile of water, and thus we get the velocity of fluid water flow in each layer of water, and thus we can. After getting this data, we can calculate heat transfer coefficient, Nusselt number, etc. Yeah, etc. from mathematical formula.
Okay, thank you. What's your name, please?
Sir, my name is Nuraldin, and I'm level 3, third year.
Okay, thank you very much. So your understanding is quite clear, and from this ANSYS we actually can exactly what he said, that we can actually calculate the thermal hydraulic parameters of reactors, and also the reactor internals, and also the fuel subchannel analysis. We can actually calculate all these parameters from ANSYS. So why we actually incorporate ANSYS? Let's have a look that in case of fluid flow, like if we consider that in the primary circuit of the reactor, the coolant is actually flowing. In that case, if we consider this case, or if we consider any real life scenario where the fluid is actually flowing, or we are considering a control volume, in that case we actually can perform two types of approaches. One is the experimental approach, another one is the calculation. So in case of experimental approach, this is not all time possible for us to actually create an experimental setup that is actually resembles the real life scenario. So you cannot actually always prepare a reactor or the primary circuit and actually flow water through this and then calculate all the parameters, because this is really quite robust, and it costs a lot. So in that case, we have to actually go through this prototype calculation, and at first we actually create the same scenario like the real life scenario in our ANSYS, and then we calculate the parameters, and we try to find some similitude between those parameters. So what we actually do in ANSYS, at first let me take an example. So this is actually a physical model for AP 1000 reactor. In AP 1000 reactor, the fuel pins, they are actually arranged in a square array, and you can see from here that the fuel pins are actually arranged in a square array, and there are 4 fuel pins, and we are actually considering this single subchannel of this AP 1000 reactor fuel assembly. And in this single fuel subchannel, the water will actually flow, and it will take the heat, it will be heated, and then in the secondary circuit, it will transfer the heat with the steam generator. So in this case, the real life length of this AP1000 reactor fuel subchannel is almost close to 3.58 meter. But in case of ANSYS, if we take a subchannel length that is actually 3.58 meter, then in that case, it will really cost us a lot of time. It will cost us really a lot of computational time. So what we will actually do, we actually do some scaling. And have you actually seen any model and prototype course? Can you remember how many of you have taken fluid mechanics course so far? Can anyone please answer, or have you heard this word model and prototype?
Yes, sir.
Okay, so can you please say that what is actually model and what is actually prototype? Okay, I'm
Is
explaining.
actually a real version, and model is like just a small version of this real scenario.
Yeah, thank you very much. So what we actually do here in the ANSYS, we also do the same thing. We actually cannot take the whole fuel subchannel length, that is 3.58 meter, because it will take a lot of computational time. So with the formulas that we have seen in your fluid mechanics course, with those formulas, we calculate the model length, and obviously its ratio, and the model length will be smaller than the prototype length, and then we actually take a specific model length, and then we take the calculation. So one thing before actually modeling into the ANSYS, we have to keep in mind that whenever we are taking the geometrical parameters of the model, it must be calculated carefully with respect to the prototype. It's not like that we have taken some arbitrary geometry. We cannot do that. We have to make those parameters of the model and the prototype. So we can see here a single fuel subchannel of AP1000 reactor, and you can see this is the single fuel subchannel, and here we have actually taken a length of 600 millimeter. 600 millimeter. So this is close to 0.6 meter. So we have actually taken a very small length, but this small length should be enough to create a fully developed flow within this subchannel. So we have to consider various things before actually modeling a geometry into the ANSYS. So this is our single fuel subchannel, and these are the boundary conditions, and these are the different parameters. We will actually come to these things later on. So what we have actually learned that at first we have to create a model, and then we have to go step by step. So what we actually do in ANSYS, does anyone have the idea about these equations? Can someone please respond?
Momentum conservation equation.
Have you seen it before?
Yes, sir. Fluid mechanics in fluid mechanics course.
Okay. So, so what we actually do in ANSYS, or in the computational fluid dynamics, to get the global properties and the integral properties of a certain computational domain. In our case, this is our computational domain, a single fuel subchannel, and we have taken a certain length of this subchannel, and this is our computational domain. And in that computational domain, we have got sets of equations, and these sets of equations actually give us an idea that what will be our global properties and what will be our integral properties within that computational fluid domain. So that's how we actually perform the thermal hydraulic analysis. Whenever we get the global properties and whenever we get the integral properties of a computational fluid domain, then we have a clear understanding about the thermal hydraulic parameters of that fuel subchannel. So to get those parameters or get those properties, those global properties or those integral properties, we need to solve these sets of equations. And you can see that these sets of equations are not actually quite easy to solve. And they are partial differential equations. And these equations are responsible for laminar flow. And this equation and also these equations, these are responsible for the turbulent flows. So before we actually put these equations and into our ANSYS model, we need to know that whether our flow is laminar or turbulent. And I hope you all know who are actually in level 3 or level 4 that how we can determine the laminar flow and the turbulent flow. So you can see that in ANSYS, we solve these partial differential equations. This is the continuity equation, and these are the momentum equations. Momentum equation in x-axis, this is the momentum equation in y-axis, and this is the momentum equation in z-axis. So this is the conservation of mass for in case of turbulent flow. That is actually the continuity equation, and this is the conservation of the momentum equation. That is the most famous Navier-Stokes equation. So in case of ANSYS fluent, our main target is to solve this Navier-Stokes equation. So this is the most fundamental equation that we have to solve in case of ANSYS CFD or in case of ANSYS fluent. So this is the conservation of the energy. Whenever you are just only considering fluid flow, whenever any kind of heat transfer is not involved in that system, we just consider these two equations, conservation of mass and conservation of the momentum. But whenever there is heat transfer involved, we also consider this, that is the conservation of the energy. So in that case, we also have to solve this equation and things become more complex. So these are the fundamental equations that we actually solve in case of in ANSYS fluent. So do you have any question till now?
No, sir.
Okay. So we can actually go forward. So how do you think that to actually solve these equations, what are the approaches that we have to do? Can anyone please answer? Okay. So I'm actually moving forward that so whenever we actually try to solve these equations in the ANSYS, what we actually do, we have to discretize our computational domain into smaller parts or into smaller cells, and the whole computational domain will be actually divided or discretized into some small cells or domains, and in every domain or in every cell these equations are applied, and we actually solve these equations for every computational cell, and then we actually get an integrated result. So it means actually slicing or segregating the whole computational domain into smaller parts. So that we are actually calling the grid or the mesh. So at first, we have to segregate or divide the whole computational domain into smaller parts. That is actually called the mesh or the grid. And when we will actually perform your simulation, you will face two kinds of situation. In some cases, you will actually solve your problem two-dimensionally, and in some cases, you will solve your problem three-dimensionally. Three-dimensional one is the more complex one than the two-dimensional one, and you can see that whenever you are dealing with two-dimensional geometry, you have got this cell that is two-dimensional, and whenever you are actually dealing with three-dimensional computational domain, we have got a 3D cell or the mesh. So this whole computational domain will be divided into smaller cells, numerous smaller cells. And at first we have to segregate this, and then boundary conditions are specified. This is the second step. We have to actually create some boundary conditions, provide some boundary conditions in to solve those equations, to make those equations more simplified. You can see that here, if we take the example of a turbulent flow, and if we take the momentum equation, and you can see that in the x direction, this equation, it actually depends on one of the variable is the density of the fluid, that is rho. So if you think, or if you consider that throughout the whole computational domain, throughout the time, the density of the fluid remains constant, then the equation becomes more simplified. And if you also consider that this dynamic viscosity, or the mu, it also remains constant throughout the computational domain throughout the time, then the equation becomes more simplified. So these are the boundary conditions or the assumptions that we have to actually apply to simplify those equations. Otherwise, it will be more complex. With proper assumption and with proper boundary conditions, we have to simplify these equations, and then we will have a better result and with reduced time. So at first we have to segregate the whole computational domain into smaller parts, and then we have to apply some boundary conditions. Then the type of the fluid that we are actually passing through the computational fluid domain, that is water, that can be water, air, or gasoline, whatever we take. In case of reactors, we actually take water, boron concentrated water. In molten salt reactors, we actually take molten salt as a coolant, or as the fluid that is actually passing through the computational domain. So it actually depends on your requirement, and also you have to specify the fluid properties, the temperature, density, and viscosity of the fluid that is actually passing. And the numerical parameters and the solution algorithms are also selected. What will be our approach to solve? There are different numerical methods that we can actually adopt to solve those equations, and also the starting values for all flow field variables. The starting values, that means the initial gauges that we have to actually take to solve our equation, and also whenever the solution has converged, and then we have to take different variables or the parameters that we want to calculate. So I want to repeat that first we have to discretize the whole computational domain into smaller parts. That means we have to create or generate some meshes or the grids. Then we have to specify some boundary conditions to make our equations more simplified. And then we have to introduce our coolant, that is that can be water, that can be molten salt, or water with boric acid. And then we have to create the numerical parameter and the solution algorithm, and we have to do some initial guesses, and then we have to run the simulation, and we have to see that whether it converges or not. If the solutions doesn't converge, that means if the equations doesn't converge, that we have to think that we have got some mistake in boundary condition, or we have to refine the mesh, or we have to increase the number of the meshes or the grids within the system. So what we actually calculate, we actually calculate the global properties of the flow field. What are the actually global properties? That means the universal properties, the pressure drop or the outlet temperature or the mass flow rate that we actually get from as an output from the ANSYS simulation, and then some integral properties, that means some specific temperature at some specific points, the temperature distribution, the critical heat flux. We also get these things after the simulation. So that's actually the approach that we actually follow. As I said, that if there is some energy conversion that is needed, we have to introduce conservation of the energy equation. And if there is some changes in the density, and then we have to also introduce the ideal gas flow. And we will actually eventually see that when we will actually work with ANSYS more. So at first, we actually want to give you some idea about the grid or the mesh generation, because if you can actually have a good mesh, then I think you are quite halfway done with your ANSYS simulation, because this will help you to get a very accurate result, and you can actually rely on that result if you have a good grid or the mesh. So there are actually two types of grids. One is the structured and another one is the unstructured. And you can see from here, this figure, that this one is the unstructured grid, and this one is the unstructured triangular grid, and this is the unstructured quadrilateral grid. So you will also face these two kinds of grids. One is the structured and the unstructured, and you don't have to bother that whether your grid is structured or unstructured. Sometimes we also get good output from the unstructured grids also. And for complex geometries, an unstructured grid is usually much easier for the user of the grid generation code to create. Whenever you are dealing with some complex geometries, it is quite easier to create unstructured grids, because you cannot actually formulate structured grids in all planes of your geometry whenever you are dealing with some complex geometries. When you're as the example that we have shown here, the fuel subchannel, it has also got a complex geometry. So in that case, you cannot always actually create structured grid. So another important thing that you have to also consider, that is the mesh quality. That what is the quality of your mesh? Is it skewed or not, or it's in perfect shape or not? Do you have any idea about this term, the skewness of the mesh? Can anyone please? Hello. Okay. So I'm telling that suppose let's look at this cell or the mesh. This triangular cell, it has got zero skewness. That means this is not distorted from its shape. And if you also have a look at this quadrilateral cell, it is also in this perfect shape. That means it also has zero skewness. And you can see that whenever this is distorted from its shape, we're telling that it has got high skewness. And similar case with this quadrilateral cells, it has also got high skewness. So whenever we are actually generating any kind of mesh in the ANSYS, we have to check for its quality. And there is an option in the ANSYS, I will show you, from where you can actually check the quality of the mesh, whether it is skewed or not. And we will always try to maintain a cell with very small skewness, and you can see this is the actually the parameter for the skewness. Whenever you are actually creating a mesh and you check the skewness, if it's give a value that is from 0 to 0.25, then you can say that your mesh quality is quite excellent. And if it's 0.8 to 0.94, this is acceptable, but we actually don't go to this red mark zone. We actually try to keep our skewness of the mesh from 0 to 0.25 or hardly from 0.3. So we try to keep the skewness of the mesh within this range. So if the skewness actually goes to 0.8 or 0.9, then we actually say that this is not actually acceptable. So what we are actually seeing that if you want to create a very good quality mesh, you have to have a look at this parameter very carefully, that whether your mesh is skewed or not. And remember that if you can create a very good quality mesh, you are quite halfway to have a good result in your from your computation. So you can also see here that this is actually you can see this mesh. These actually have some quadrilateral cells, but they have got high skewness. And here you can see that some triangular cells, but the skewness is very within the good range. You can see they are not distorted from their shape, and similar is the case also here and also here. So this is actually the real scenario or the mesh that we actually created in our computational domain that we have shown earlier. That is a computational domain for AP1000 reactor fuel subchannel. So you can see that on its faces here, we have actually created some quadrilateral meshes. So and also in this face, we have got actually some combined meshes. We have got some triangles, and we also have some quadrilaterals or the rectangles. And if we actually see very closely here in the boundary layer region, we also have some cells. Those actually are in rectangle shape. We cannot see it from here. They are actually highly dense. So we can see that this mesh quality is quite good. We have got very small skewness. These shapes are not distorted. So we will actually try to create this good quality mesh. So one of the limitations of ANSYS student version is that you cannot actually create this high amount of nodes or the cells within your computational domain. The more you increase the number of the nodes or the cells, the more accurate will be your result. Remember, if you increase the number of the nodes or the cells within your computational domain, then you will have a better result. If your node number or cell number is not very high in your computational domain, then your solution is less likely to converge and your solution will not be that much accurate. So remember these 2 points. When you are creating a mesh, try to increase the mesh number or the grid number as much as you can, and also have a close look at the quality of the mesh, whether the meshes are skewed or not, whether the shape of the meshes or the cells are distorted or not. If they are distorted from their original shape, then your result will actually vary. So what is actually happening? We actually divided our computational domain into these smaller cells or the grids, and then we will solve those energy equation, momentum equation, and continuity equation that we have seen earlier, and we will solve those equations within these cells, within every cell, and then we will have a have an integrated result. So this is actually the basic approach of this computational fluid dynamics. In real life scenario, the same thing happens, but we actually cannot create a real scenario every time. So we actually simulate the same scenario within this computational software, and then we try to match the result that we get from our computation with the experimental one, and then we try to validate and have a conclusion that whether our result is okay or not. So let me repeat. There are some cases when we can actually perform experimental calculations. Suppose you have created a model for reactor fuel sub-channel with a very small model in your lab. This is an experimental setup. You can do that. And then you can perform your investigation on that. So this is one approach, that you create a model of the prototype in a very small scale physically, and then run your experiment in your lab with that experimental setup. And then you take some of the global parameters like the pressure drop or the mass flow rate or the outlet temperature. And from that experimental setup, you can have some global parameters that I mentioned. You can measure pressure drop, you can measure mass flow rate, or you can measure the outlet temperature. But from that experimental setup that you have created in your lab physically, you cannot measure the integral properties from that experimental setup all the time because of some constrictions, because it can be not cost-worthy, and it's difficult. Like if you want to measure the temperature at a specific point in your fuel sub-channel, or if you want to measure the critical heat flux in your experimental setup, or if you want to measure the you want to have the profile of the heat distribution, profile of the velocity distribution in your experimental setup, you cannot do that or get those results directly from your experimental setup. So what we actually do, we actually create the same experimental setup from in your ANSYS Fluent software, and then you give all the same parameters that you have given in your experimental setup, and then you run the simulation and you match the global properties that you have found from your ANSYS simulation with the properties, with the global properties that you have found from your experimental setup. You try to match. If they match, if these values are within the closed range, then you can say that your computational fluid dynamic result, or the ANSYS fluid result, is accurate, and you can use it for further use. And remember, without validation with the experimental data, these computational fluid dynamics values are not independently, cannot be independently used. If you do any thesis, if you do any research papers, if you want to publish any scientific journal, remember that you have to validate these results that you get from your computational fluid dynamic with the experimental one, or some calculations that was run earlier in the CFD software by some other researchers. And if these global parameters match with your experimental one, then you can actually take the integral properties, or you can take the velocity profile, you can take the temperature distribution, or numerous properties that you want to take, or you can then you can say that yes, these results, these integral parameters also be accurate. So did you get my point?
Yes, sir.
Yes, sir.
Okay, so this is a very important step when you are actually performing ANSYS, that you cannot actually rely 100% on ANSYS data. You have to actually validate them with some experimental ones. So, and then what you have to do, that you have to perform the grid independent test. So you can say that how many grids I have to generate. It can be 1 million, it can be 2 million, it can be 10 million. So as you can say that you have said that the more you have grid, the more accurate result you have. So what is the limitations of the grid number? So at this point, you have to perform the grid independent test. What do you have to actually do? That if you take 50,000 nodes, or if you take 50,000 cells or grids, and you see that your solution is converged, for reference, okay, so you can say that with this 50,000 nodes, your solution is converged. And you can see that if you take and increase the node to 60,000, and you still see that your solution is converged. But in your earlier calculation, when you actually took a node of 50,000, and you see that your pressure drop was 50 Pascal, but whenever you are actually increasing the node to 60,000, you see that your pressure drop has become now 40 Pascal. So by increasing the node, you can see in both cases your solution is being converged, but your desired value, it's actually fluctuating, it's changing. Then what you have done, you have actually increased the node to 70,000, and your solution is still converged, but you get a pressure drop value of 30 Pascal. So you're quite confused that that you may say that with the increasing node, my pressure drop value, it is actually fluctuating. Then what you have to do, you have done that you have taken 80,000 nodes, and then you have seen that your solution converging, but the pressure drop value is close to the previous one, that is 30 Pascal. And then you have increased the node to 90,000, and still you have seen that the pressure drop value is 30 Pascal. And you have taken 1 lakh node, and you can see that the pressure drop value is still 30 Pascal. So you can see that when you have taken 70,000 node, your pressure drop value has become fixed. It's not fluctuating anymore. So at that time, you can say that after this 70,000 node, your solution is grid independent, that your solution does not depend on the number of the grid or the nodes that you have chosen. So for 70,000 node, you have this 30 Pascal of pressure drop value. For 80,000 node, you have also this 30 Pascal of pressure drop value, and for 90,000, you also have this 30 Pascal pressure drop value. So what is the node number that I have to choose? Can you please tell? Anyone, please?
Sir, minimum 70,000, but it will better than yeah, more will be better.
Okay, yeah, he's quite correct, because we have to take minimum 70,000. If we take more, it's I think if the value doesn't fluctuate that much, it's not advisable to take more, because it will actually increase the computational time, and in some cases the computational cost also. So to actually avoid that, we actually take this minimum value, after which our solution actually becomes quite constant. So this is up to this grid independence test. You have what are the approaches that I've already discussed. That at first you have to create a model. Have to create a model. This model must be analogous to the model that you have created in your lab, or this model is actually a model of a prototype of a large scale commercial facility, and you have to create the model by taking all the requirements of model and prototype that we have that you have learned in your previous classes or in previous courses. And then we have to create the geometry in the ANSYS. To create the geometry in the ANSYS, this is simple. All of you have used AutoCAD or SolidWorks. This has got the same interface. You have to create the geometry, and after creating the geometry, then you have to create the mesh. And while creating the mesh, the things that we have to consider, we have said that you have to consider the quality of the mesh, and also you also have to have a close look at the number of the mesh of the grid that you have to produce. Then you have to perform the grid independence test. So this is so far the procedure. And one thing that in addition, I'd like to say that if you want to create a mesh, and sometimes there are some boundary layer regions. There are some flow development regions. And in that case, we have to bring or consider additional issues. And you may think that I am creating some grid or the meshes, but what will be the thickness of the grid, or what will be the length of the one arm of the grid? What will be the geometric dimension of that cell or the grid or the node? In that case, to specify the geometric dimension of that node or cell, you have to consider some certain issues. Like if there is any flow development issues, if there is some boundary layer development consideration, then you have to take node thickness or node dimension in such a way that it doesn't cross the boundary layer thickness. Otherwise, you not get a good result. So these are the issues that you will actually encounter when you do a real life project. So I want to now show you some example of a project that is that I have created for you. You can see this is the interface of the ANSYS, and whenever you install ANSYS and you open it, you have to open the ANSYS workbench. Sometimes when you try to open the ANSYS from your laptop or desktop, you cannot find the ANSYS option directly. You have to search for workbench. And here I'm dealing with ANSYS 16. You have to open this workbench, and then you can see that there are lots of options that you can simulate in ANSYS. There is some fluid flow, blow molding. There is some harmonic responses, IC engine. If we get some time, maybe in another classes or maybe in another course, we can talk about this IC engine part of ANSYS software. This is quite interesting, and it has got a whole new dimension. And we have got thermal electric coupling options here, steady state thermal, and also you can do some steady state abacus calculation also here. But in our case, we will take ANSYS Fluent. That is actually widely used for performing the CFD analysis in ANSYS. And when you select it, there are these options will come, and this is at first you have to create the geometry, and there is then the mesh that we have seen. Then you have to do the setup. That is actually the next step. What we are going to do maybe into this class or next class. That after creating the mesh, you have to incorporate your boundary conditions, and also you have to choose some solution algorithm, some solution models based on laminar flow or the turbulent flow. We actually choose some of the models that we want to solve those equations. And then we run the simulation, and then we get the solution part. This is the result of the post-processing that we, if you want to take the temperature distribution profile, if you want to take the velocity distribution profile or the heat flux, and these results will be there. And this is the parameter part. If we want to calculate some additional parameters, that we can actually calculate it from here. So at first, let me go to the geometry. If you double click here, this geometry part will be opened. So here is my geometric part. This is not that much difficult one. You can see that here. We have actually created a sub-channel, fuel sub-channel from here. And in this sub-channel, what we have actually seen that these are the faces that is in contact with the fuel pin. These are the faces that is in contact with the fuel pin, and these are the faces that is not in contact with the fuel pin, that is actually open to the water and adjacent to the surrounding fuel sub-channel. So what we have actually done here, that we have actually created plane or the mark here, because after this region, we have got the fully developed flow region. If the flow actually enters through this inlet, and after this length, we have got a fully developed flow region, and this is our entrance length. And in our case, we had to actually calculate this fully developed region and the entrance length region. So we actually had to consider that. And the next part is the mesh part that we want to see, that the mesh that we have actually created. We can actually discuss it in this class, or also maybe we will continue our discussion in the next class also. But one thing that we'd like to mention, that in commercial industry, if you talk about some famous designers of the reactors and the reactor pressure vessels like General Electric or the Gidropes, they also used to use this software ANSYS for actually designing their reactor pressure vessels, because it's not all the time that you build the reactor pressure vessel and then you do the calculations. At first, you have to create a same model like a real life prototype of the reactor vessel, and you have to consider the different parameters there. Then you actually execute it to create the real reactor pressure vessel. So both the General Electric and also the Gidropes, who is the designer of the VBR 1000 and VBR 1200, they actually use this same software ANSYS till today to actually calculate the thermal hydraulic part of designing the reactor pressure vessel. Nowadays, they also use COMSOL, but COMSOL is actually specified and good for some other sectors, like if you for some electromagnetic calculations or some other calculations where we have got multiple things involved. But for this thermal hydraulic part analysis, this is quite enough. This part is quite enough, this ANSYS. So this is so far the saying from me for today's class. Do you have any question? You can ask, please. I actually tried to give you the fundamentals, because step-by-step process you can actually find it in different tutorials or in some other resources. But the basic understanding and the fundamentals, you need to actually have a strong belief in that, so that you don't actually make mistakes when you are dealing with the ANSYS. So do you have any question? I know it's difficult because it's your midterm vacation and you still are enrolling this course, because I believe that you are quite interested and enthusiastic. So does it meet your requirement, or what did you expect actually? You can actually give your feedback, please.
Sir, how can I download this ANSYS software?
Okay,
I
I
can
will
understand your lecture, but
okay,
yes,
I
sir.
will actually share another link today in the WhatsApp. You can download it from there, and obviously by today you can download it.
Sir,
And
it will be
practice.
easier for me if you provide any video link actually, because the torrent.
Mhm.
How can I download from torrent link? I don't know actually.
Okay, I will give the demonstration of the video today, and also I will give you a simple practice problem in the WhatsApp group, so that after downloading that software and installing it, you can actually keep practicing.
Thank you, sir.
Okay. Anyone wants to share any thought? Have anyone done any project in ANSYS so far from this group? Okay, so if you don't have any question, I think we can actually conclude our session for today, and tomorrow at 10 we actually meet again. And today I will actually give you the link to download and practice. And there are some Linux users who actually wanted to have a guideline, but it actually takes a lot of time to actually guide them on an ANSYS. The Linux users, I think you can start practicing OpenFOAM. That is very similar to the OpenMC. Some of you have worked with OpenMC also. And this OpenFOAM, this is widely used in the worldwide for computational fluid dynamics. That is less user-friendly, but you can use that. And if you face any difficulties, you may contact with me at any time. There are lots of experts in OpenFOAM throughout the world. You can actually connect through them. So the Linux users, you can use OpenFOAM, and you can actually search it and actually can have a good understanding on that. And for Windows and the Microsoft users, this ANSYS, this is actually quite a convenient one. It has got a very convenient user-friendly interface, and we have got lots of premeditated equations and characteristics and boundary conditions that we can actually put easily. So thank you very much, everyone. I can conclude, or I would like to hand over the floor to the moderator of the club, or the person who is actually responsible. Thank you.
Assalamu alaikum, sir. Thank you, sir.